Somewhere in the dark between planets, a frozen traveler is quietly drifting toward the sun. It has waited, perhaps, for thousands of years in the deep cold beyond Neptune, a small island of ice and dust no larger than a city. And now, slowly, almost imperceptibly, it begins to wake. As sunlight touches its ancient surface, it releases a long, luminous tail that stretches across millions of kilometers. Tonight, as you settle into stillness, we will follow these wanderers, the comets, across the silent reaches of our solar system, and let their slow, eternal journey carry you gently into sleep. Welcome to Let's Learn While You Sleep. Tonight, we drift outward, far beyond the warmth of Earth, into the great dark sea of our solar system, where icy travelers move on patient, ancient orbits. Comets are some of the oldest objects we can see, fragments left over from the birth of the planets, preserved in deep cold for billions of years. They are messengers from the beginning of things, carrying within them the chemistry of a young sun and the dust of a forming world. Across this quiet hour, we will explore where comets come from, how they are made, why they grow their luminous tails, and what they may have given to the early Earth. There is nothing for you to do, nothing to remember. Let your breathing slow, let your shoulders soften, and allow these distant drifting wanderers to carry your thoughts gently outward into the calm and starlit dark. To understand a comet, we must first imagine the place where most of them were born. Roughly 4.5 billion years ago, our solar system was a swirling disk of gas and dust, slowly condensing around a newborn sun. Closer in, where temperatures were warm, rocky worlds began to form: Mercury, Venus, Earth, and Mars. But farther out, beyond the orbit of what would become Jupiter, the disk was cold enough that water, methane, and ammonia could freeze into solid grains. These icy specks drifted, collided, and slowly stuck together, forming larger and larger bodies. Some grew into the cores of the giant planets. Others remained small, frozen survivors of a more chaotic age. These small icy bodies, only a few kilometers across, are what we now call comets. They are, in a sense, the leftovers of creation, untouched by the heat and weathering that reshaped the inner planets. Locked inside their dark crusts are the original molecules of the early solar system, preserved as if in a deep freezer for nearly the entire age of the universe. When astronomers study a comet, they are reading a record older than Earth itself, a chemical letter written before the oceans, before the continents, before the first cell stirred to life. And yet, despite their ancient origins, comets are not motionless. They move, slowly and silently, on enormous orbits that can take them far beyond the planets, into regions so dark and so cold that the sun itself is just another faint star. Some return every few years. Others vanish for tens of thousands of years before falling, once again, toward the warmth at the center of everything. Tonight, as you rest, picture one of these tiny worlds, drifting in the absolute stillness of deep space, its surface darker than coal, its interior holding the frozen breath of a forming solar system. It has been waiting longer than you can imagine, and it is patient. Now let us move outward, far beyond the planets, to one of the most mysterious regions of our solar system. Astronomers call it the Oort Cloud, named after the Dutch astronomer Jan Oort, who proposed its existence in 1950. The Oort Cloud is believed to be a vast, roughly spherical shell of icy bodies surrounding the Sun at distances perhaps as great as 100,000 times the distance between Earth and the Sun. To picture this, consider that light from the Sun, which crosses the Earth's orbit in only 8 minutes, may take more than a year to reach the outer edge of the Oort Cloud. It is the true frontier of our Sun's influence, the place where our star's gravity finally fades into the gravity of other stars. We have never directly seen the Oort Cloud. It is too distant, its members too small and too dark. Its existence is inferred from the orbits of long-period comets, which arrive from all directions in the sky and carry signatures of having traveled from enormous distances. Current evidence suggests that trillions of cometary nuclei may drift in this distant shell, each one a quiet world of ice and ancient dust. Out there, the temperature hovers only a few degrees above absolute zero. The Sun, if you could see it from such a distance, would appear as little more than a particularly bright star, no warmer than candlelight at the far end of a vast hall. Comets in the Oort Cloud move slowly, almost imperceptibly. They drift for ages, untouched, until something disturbs them. Perhaps the gentle gravitational nudge of a passing star, or the slow tide of our galaxy itself. When that happens, a comet's orbit may shift, and it may begin a journey lasting many thousands of years toward the warmth and light of the inner solar system. Tonight, imagine that distant cloud, silent and immense, holding within it the patient seeds of countless future comets, waiting in a darkness so deep it almost feels like sleep. Closer to home, there is another reservoir of comets, one that lies just beyond the orbit of Neptune. It is called the Kuiper Belt, named after the astronomer Gerard Kuiper, who in 1951 proposed that such a region might exist. Unlike the Oort Cloud, the Kuiper Belt is not a vast spherical shell, but a flattened ring, lying roughly in the same plane as the planets. It begins at about 30 times the Earth-Sun distance and extends outward to perhaps 50 times that distance. Within it drift countless icy bodies, some large enough to be considered dwarf planets like Pluto, Haumea, and Makemake, and others much smaller, perhaps only a few kilometers across. From the Kuiper Belt come what astronomers call short-period comets, comets that take less than 200 years to complete a single orbit around the Sun. These are the comets we tend to know best because they return again and again, allowing us to watch them brighten, fade, and reappear across human lifetimes. Halley's Comet, which graces our skies roughly every 76 years, is the most famous of them all, a faithful visitor whose passages have been recorded by civilizations for more than 2,000 years. The Kuiper Belt is cold, but not as cold as the Oort Cloud. Its members move in more orderly orbits, gently shaped by the gravity of the giant planets, especially Neptune. Sometimes, gravitational interactions can nudge a Kuiper Belt object inward, sending it on a long fall toward the Sun. Slowly, over centuries, it crosses the orbits of the gas giants, occasionally swinging close to one of them, sometimes being slingshot into a new path. And eventually, if conditions are right, it becomes one of the comets we see streaking across our skies. Tonight, picture this distant ring of icy worlds, turning slowly in the dark, each one a quiet sphere of frozen water and dust. They have been turning for billions of years. They will keep turning long after we are gone. There is something deeply restful in that thought. Let us now turn our attention to the comet itself, to the small dark world at the heart of all this drifting beauty. The solid body of a comet is called the nucleus, and it is, in many ways, the strangest kind of object in the solar system. A typical cometary nucleus is only a few kilometers across, often shaped irregularly, like a peanut, a potato, or a tumbling fragment of stone. It is composed primarily of water ice, mixed with frozen carbon dioxide, methane, ammonia, and dust grains rich in carbon and silicate minerals. Astronomers sometimes describe a comet nucleus as a dirty snowball, a phrase first popularized by the American astronomer Fred Whipple in 1950. It is a useful image, though perhaps not entirely accurate. Modern measurements suggest that many comet nuclei are darker than fresh asphalt, reflecting only a few % of the sunlight that falls on them. So perhaps we should picture them not as bright snowballs, but as soot-covered icebergs, blackened by a long exposure to cosmic radiation, hiding pale, pristine ice just beneath their surfaces. When a spacecraft has visited a comet, as the European Space Agency's Rosetta mission did with Comet 67P Churyumov-Gerasimenko in 2014, we have seen these worlds up close. The surface is rugged and complex, dotted with cliffs, pits, and dunes of fine dust. Jets of vapor rise from cracks where sunlight has warmed the ice below. The nucleus is not a smooth sphere, but a strange, fragile landscape, sculpted slowly by the loss of its own substance over countless orbits. Each time a comet swings close to the Sun, it sheds a little more material into space, sometimes only a few meters of ice and dust from its surface. And over many passes, this slow erosion can change its shape, weaken its structure, or even break it apart. Tonight, imagine standing on such a surface, in shadow, looking up at distant stars. The silence so complete, you could hear your own thoughts settle, like dust upon ancient ice. Now let us follow a comet on its long, slow journey inward, from the frozen edges of the solar system toward the warmth of the Sun. For most of its life, a comet drifts in profound darkness, in temperatures so low that the molecules within it barely move at all. Out there, beyond the orbit of Neptune, sunlight is little more than a distant pinprick, a star among stars, offering no real warmth, no measurable heat. The comet is, in every sense, asleep, a quiet body of ice and dust, suspended in the great silence between worlds. And yet, across millions of years, gravitational nudges accumulate. A passing star, a slow tug from the galaxy itself, the gentle pull of distant Jupiter. Any of these can alter the comet's path, bending it inward by some impossibly small angle. That tiny change is enough. Once redirected, the comet begins a fall that may take tens of thousands of years to complete, sliding silently down the gravitational slope of the sun. As it falls, it gathers speed. The light around it grows slowly brighter. Stars that once seemed fixed begin, ever so slightly, to shift their positions. Somewhere in that darkness, the comet crosses an invisible threshold, the place where sunlight first becomes warm enough to matter. Astronomers sometimes call this the frost line, though for comets the more meaningful boundary is roughly the orbit of Jupiter, where solar warmth begins to wake the sleeping ices. There, water ice, the most abundant frozen substance in the comet, starts to sublimate, passing directly from solid to gas without ever becoming liquid. Tiny jets of vapor escape from the surface, carrying with them grains of ancient dust. The comet, after eons of silence, has begun to breathe. It is a slow awakening, almost imperceptible at first. But with each passing day, as the sun grows larger in the comet's sky, more ices stir, more vapor lifts, more dust drifts free. A faint glow begins to surround the dark nucleus, soft and diffuse, like a candle held behind frosted glass. This soft glow has a name. Astronomers call it the coma, from the Latin word for hair, and it is one of the most beautiful features a comet possesses. The coma is a vast, tenuous atmosphere of gas and dust, surrounding the small icy nucleus like a luminous halo. Though the nucleus itself is rarely more than a few kilometers across, the coma can swell to enormous size, sometimes reaching diameters of 100,000 kilometers or more. Larger, in some cases, than the planet Jupiter. And yet, despite its great size, the coma is extraordinarily thin. It is far less dense than the best vacuum we can create here on Earth, a whisper of gas spread across an immense volume of space. The light it emits comes from two sources, each gentle in its own way. Some of it is simply reflected sunlight, bouncing off the countless dust grains that drift within the coma, but some of the light is produced by the gas molecules themselves, energized by ultraviolet radiation from the sun, and re-emitting that energy as a faint, glowing fluorescence. Different molecules glow in different colors: water vapor, carbon monoxide, cyanogen, hydroxyl, each contributing its own subtle hue to the comet's luminous veil. To the naked eye, of course, these colors blend into a soft, milky white, sometimes tinged with the faintest hint of green or blue. Surrounding the visible coma is something even larger, though invisible to human eyes. It is a vast cloud of hydrogen atoms, produced when sunlight breaks apart water molecules released from the comet's surface. This hydrogen envelope can extend millions of kilometers into space, dwarfing even the bright coma itself. We cannot see it without specialized ultraviolet instruments, and yet it is there, a quiet ghost wrapped around the comet, a testament to how much water these ancient travelers carry. Consider for a moment what this means. A small dark body, only a few kilometers wide, can clothe itself in an atmosphere larger than a planet, simply by warming gently in the light of a distant star. And yet the coma is only the beginning of the comet's transformation. As the icy traveler continues to fall toward the inner solar system, sunlight grows stronger still, and a new feature begins to unfurl behind it: the tail. In fact, most comets develop not one tail, but two, each shaped by a different kind of force, each pointing in a slightly different direction. The first is the dust tail. As gas escapes from the comet's surface, it carries with it tiny grains of dust, ranging in size from microscopic specks to grains as large as a grain of sand. These dust particles are gently pushed by the pressure of sunlight itself, a subtle but persistent force known as radiation pressure. Because the dust grains have mass, they respond slowly, curving away from the comet in a graceful arc that traces the comet's recent path through space. Seen from afar, the dust tail often appears yellowish or white, glowing softly with reflected sunlight. And it can stretch for tens of millions of kilometers across the sky. The second tail is more ethereal. It is the ion tail, sometimes called the gas tail or the plasma tail. As ultraviolet sunlight strikes the gases in the coma, it strips electrons from some of the molecules, leaving them electrically charged. These ions are then caught by the solar wind, the steady stream of charged particles flowing outward from the sun, and carried away in a thin, straight tail that always points directly away from the sun, regardless of the comet's direction of motion. The ion tail glows with a delicate blue color, a hue produced largely by ionized carbon monoxide molecules fluorescing in the sunlight. Where the dust tail curves like a ribbon, the ion tail extends straight and slender, a cosmic windsock revealing the invisible flow of the solar wind. Together, these two tails create the iconic image of the comet, a luminous head trailed by streamers of gold and blue, sweeping silently across the night sky, a sight that has captivated human eyes for as long as we have looked upward. Throughout history, the appearance of a bright comet has been one of the most striking events in the human sky. Long before we understood what comets truly were, people across many cultures recorded their passing, sometimes with awe, sometimes with apprehension. The Chinese kept particularly meticulous records, with observations of comets going back more than 2,000 years, carefully noting the date, the position among the stars, and the shape of each tail. These ancient records remain valuable to astronomers today, allowing us to trace the orbits of certain long-period comets across centuries. One comet in particular has woven itself deeply into human history, Halley's Comet, named for the English astronomer Edmund Halley, who in 1705 proposed that several historical comet sightings, separated by roughly 76 years, were in fact appearances of the same object returning on a regular orbit. Halley predicted that the comet would return in 1758. He did not live to see his prediction confirmed, but on Christmas night of that year, the comet was sighted once again, exactly as he had foretold. It was a triumph of Newtonian physics, a vivid demonstration that even these mysterious wanderers obey the same gravitational laws that govern the planets. Halley's Comet has been observed at every return since, most recently in 1986, and it is expected to grace our skies again in the year 2061. Other comets have left their own marks on history. The Great Comet of 1577 was studied carefully by the Danish astronomer Tycho Brahe, whose measurements helped prove that comets travel far beyond Earth's atmosphere, through the realm of the planets. The bright comet Hale-Bopp, visible to the naked eye for many months in 1996 and 1997, became one of the most widely observed comets in modern times. And every so often, a comet appears that no one expected, discovered only weeks or months before its closest approach to the Sun, a reminder that the outer solar system still holds countless travelers we have yet to meet. Each comet, in its own quiet way, carries a story written in ice across deep time. In ancient China, astronomers kept some of the most meticulous comet records the world has ever known, carefully cataloguing these visitors across more than 2,000 years of observation. Their scrolls describe comets as broom stars, sweeping the heavens with luminous tails, and they distinguish them from ordinary stars with remarkable precision. Some of these records, preserved in silk and stone, have helped modern astronomers trace the orbits of comets that returned again and again across the centuries. In medieval Europe, the appearance of a comet was often interpreted through a different lens, seen as a portent of war, plague, or the death of kings. The Bayeux Tapestry, woven in the 11th century, famously depicts what we now know as Halley's Comet, hanging above the heads of astonished onlookers, just months before the Norman conquest of England in 1066. People pointed at the sky in wonder, uncertain whether to feel awe or dread. And yet, even in those uncertain times, there were minds gently turning toward understanding. Across the centuries, observers slowly began to realize that comets were not omens at all, but objects, real things, traveling along paths that could be measured and predicted. The breakthrough came in the late 17th century, when the English astronomer Edmund Halley applied Isaac Newton's new laws of gravity to the records of past comets. He noticed something extraordinary, that the comets observed in 1531, 1607, and 1682 followed nearly identical paths, separated by roughly 76 years. Halley proposed that these were not three different comets, but a single comet returning, again and again, on a long elliptical orbit around the Sun. He predicted it would return in 1758. Halley did not live to see that prediction confirmed, but on Christmas Day of that year, the comet appeared once more in the night sky, exactly as he had said it would. From that moment on, comets ceased to be omens. They became members of the solar system, governed by gravity, and the comet that returned for Halley still bears his name today, faithfully passing by Earth roughly once each human lifetime. Today, astronomers divide comets into two broad families, distinguished mainly by the length of their journeys around the Sun. The first family is known as the short-period comets, those that complete an orbit in less than 200 years. Halley's comet belongs to this group, as does the smaller, fainter comet Encke, which returns roughly every 3 1/3 years, the shortest known orbit of any comet. These short-period comets are believed to come from a vast, disc-shaped region beyond the orbit of Neptune, called the Kuiper Belt. The Kuiper Belt is a cold, distant ring of icy bodies, stretching from about 30 to 50 astronomical units from the Sun, that is, 30 to 50 times the distance between Earth and the Sun. There, in that quiet outer twilight, countless small worlds drift slowly through space, occasionally nudged inward by gravitational interactions with the giant planets. The second family is the long-period comets, whose orbits can stretch across thousands or even millions of years. These come from a far more distant and mysterious region, known as the Oort Cloud. Named after the Dutch astronomer Jan Oort, who proposed its existence in 1950, this cloud is thought to be a vast spherical shell of icy bodies surrounding the entire solar system, perhaps reaching as far as 100,000 astronomical units from the Sun, almost a quarter of the way to the nearest star. The Oort cloud has never been directly observed. Its existence is inferred only from the long, randomly oriented orbits of the comets that fall inward from it. And yet, if current models are correct, this cloud may contain trillions of cometary nuclei, drifting silently in the deep cold of interstellar space. Imagine, for a moment, that vast, invisible halo, far beyond the planets, far beyond even the heliosphere, a sphere of ancient ice in the dark. Every now and then, the gravitational tug of a passing star, or the slow churning of the galaxy itself, sends one of these frozen wanderers tumbling sunward, beginning a journey that may take 1,000,000 years to complete. To truly understand a comet, however, one must do more than watch it from afar. One must visit it. And in the late 20th and early 21st centuries, humanity began to do exactly that. In March of 1986, a small armada of spacecraft, sent from different nations, flew through the coma of Halley's Comet during its most recent passage near the Sun. Among them was the European Space Agency's Giotto probe, which passed within about 600 kilometers of the comet's nucleus and returned the first close-up images ever taken of one. What Giotto revealed was startling. The nucleus of Halley's Comet was not a bright, gleaming snowball as many had imagined, but a dark, irregular, peanut-shaped body, blacker than coal, jetting plumes of gas and dust from active regions on its sunlit side. It was, in the words of one astronomer, the darkest object yet observed in the solar system. 2 decades later, in 2014, an even more ambitious mission unfolded. The European spacecraft Rosetta, after a journey of more than 10 years, arrived at a comet with a long and difficult name, 67P/Churyumov-Gerasimenko. Rosetta did not merely fly past. It entered orbit around the comet and traveled with it for over 2 years as the comet approached and rounded the Sun. And in November of 2014, Rosetta released a small lander named Philae, which became the first human-made object ever to softly touch down on a comet's surface. The images Philae and Rosetta sent back were astonishing. A strange, double-lobed world of cliffs, dunes, and dust, with sharp shadows and surprising landscapes. Rosetta detected complex organic molecules in the gases venting from the surface, including amino acid precursors, the chemical building blocks associated with life. The mission deepened a possibility that scientists had long considered, that comets, throughout the early history of Earth, may have delivered water and organic compounds to our young, hot planet. It is possible, though not yet proven, that some of the very molecules in your body once rode through space inside a frozen comet, billions of years ago. Consider for a moment what that means. The water that fills the oceans, that falls as rain, that you have sipped countless times throughout your life. Some fraction of those molecules may have arrived on Earth aboard comets during a chaotic period in our planet's youth, known as the Late Heavy Bombardment. Current evidence is mixed. Measurements of the ratio of deuterium, a heavy form of hydrogen, in cometary water suggest that not all comets share the chemical fingerprint of Earth's oceans. Some comets, like 67P, contain water with a deuterium ratio quite different from ours, while others, observed by telescopes such as Herschel, show a closer match. The picture remains incomplete, and most scientists now believe that Earth's water came from a mixture of sources, perhaps mostly from asteroids in the outer asteroid belt, with comets contributing a smaller, but possibly significant, share. What is clearer is that comets are rich in organic chemistry. They carry carbon, nitrogen, hydrogen, oxygen, the elemental ingredients of biology, bound together in complex molecules forged in the cold of deep space. Whether or not comets seeded life on Earth, they certainly carried materials that life would later use. They are, in a sense, ancient libraries of chemistry, preserved in ice for over 4.5 billion years. And every time one falls inward toward the sun, every time its tail unfurls across the dark sky, it is releasing a small portion of the early solar system back into space, a faint, glowing memory of how everything began. There is something deeply restful in this thought, that the same ingredients which now lie within your body, the same atoms in your blood and bones, may have once drifted through frozen blackness for unimaginable spans of time. That you are, in a quiet, literal sense, kin to the comets, made of similar stuff, gathered from similar dust, warmed by the same patient sun. And as you continue to drift towards sleep, perhaps that thought can settle gently within you, like falling snow upon a still and silent field. And so, in the late 20th century, a remarkable idea began to take shape in the minds of planetary scientists. If we wish to know what built the worlds, we should not only study comets through telescopes from afar. We should go to them, we should fly alongside them, photograph their nuclei, taste their dust, and even, if we dared, land upon their fragile surfaces. The first true encounter came in 1986, when a small fleet of spacecraft from several nations flew past Halley's comet during its return. Among them was the European Giotto probe, which passed within roughly 600 kilometers of the nucleus, returning the first images humanity had ever seen of a comet's solid heart. What it found astonished the world. The nucleus was not a clean white snowball, as many had imagined, but a dark, irregular body, blacker than coal, shaped something like a peanut, only about 15 kilometers long. Its surface absorbed nearly all the sunlight that fell upon it, hiding the bright ices beneath a crust of complex carbon-rich material. From this dark surface, jets of gas and dust erupted on the sunlit side, fountains of vapor escaping through cracks in the crust. The image was strange, beautiful, and humbling. Then, decades later, came an even bolder mission. In 2014, after a journey of more than 10 years and roughly 6 billion kilometers across the solar system, the European Space Agency's Rosetta spacecraft arrived at Comet 67P Churyumov-Gerasimenko. It did not merely fly by. It slowed, matched the comet's motion, and entered orbit, becoming the first probe ever to circle a comet through the long approach toward the Sun. And in November of that year, Rosetta released a small lander named Philae, which descended through the comet's faint gravity and touched down upon the surface, a feat that had never before been attempted. For the first time in history, a machine built on Earth rested upon a wandering ice mountain, listening to its quiet murmurs, sensing its trembling skin, watching the stars wheel slowly above an alien horizon shaped over 4.5 billion years. What Rosetta and Philae revealed was a world more strange, more delicate, and more ancient than anyone had truly expected. Comet 67P was shaped like a small rubber duck, two rounded lobes joined by a slender neck, tumbling slowly through the dark. Its longest dimension stretched only about 4 kilometers, smaller than many cities, and yet across its surface lay a landscape of extraordinary variety. There were cliffs hundreds of meters tall, smooth dust-covered plains, pits that seemed to breathe out gas, boulders the size of houses balanced upon icy slopes, and dunes carved somehow by the comet's whisper-thin atmosphere of escaping vapor. Gravity there was almost nothing at all. A person standing on its surface, were such a thing possible, could leap into the sky and never return, drifting upward into orbit with the lightest push. Instruments aboard Rosetta sniffed the gases rising from the nucleus and found a rich mixture: water vapor, carbon monoxide, carbon dioxide, methane, ammonia, formaldehyde, and a quiet surprise: molecular oxygen, a gas that had not been expected and whose presence still puzzles researchers today. Even more striking, the spacecraft detected complex organic molecules, including the simple amino acid glycine, one of the building blocks of proteins. Glycine, drifting in the breath of a comet, 4 billion years old, far from any living thing. This discovery did not prove that comets seeded life on Earth. That remains a hypothesis, debated and refined, neither confirmed nor dismissed. But it strengthened a quiet, beautiful possibility that the chemistry of life is not rare, not local, not unique to our blue world, but woven into the very fabric of the disk from which the planets were born. Somewhere in that darkness, in countless icy bodies still wandering the outer solar system, those same gentle molecules may be sleeping, waiting, drifting through cold light. And as you let your thoughts settle, consider how far that idea reaches, that the ingredients of you, of every breath you take, may once have ridden upon a comet through the silence between stars. And so, for tonight, we leave our wanderers drifting in the dark, their long orbits unfolding silently across the immense quiet of our solar system. We have traced their birth in the cold outer disk of a young sun, visited the distant shell of the Oort Cloud, glided across the slow ring of the Kuiper Belt, and stood, in imagination, upon the rugged surface of a single ancient nucleus. There is no rush in any of this. Comets keep their own time, measured not in hours or years, but in centuries and millennia. Let your breathing settle into that deeper rhythm. Let your thoughts grow quiet and slow, like a comet drifting far from the sun, untouched, unhurried, simply being. Tomorrow, if you wish, we will follow these travelers further, into their luminous awakening, the unfurling of their tails, and the gentle gifts they may have brought to the early Earth. But for now, rest. The universe is patient. And so tonight, may you be patient too, gently drifting towards sleep. If tonight's quiet journey has soothed you, consider letting it become a gentle habit. Thank you for spending your night with Let's Learn While You Sleep. Subscribe and come back tomorrow night. We'll be here. Sleep well.